In the last section, we computed areas. In section 6.3 and in section 6.4, we're going to compute volumes. We're going to first compute volumes by a method called slicing. So what we're going to do is we're going to look at some base that we'll get from our function, and then from that base we're going to create an area that we're going to integrate. Now, it doesn't mean much, these are just words until you see a picture. So the steps would be graph. Always graph. That gives you so much information. Find the formula for A of x. And what we're going to call A of x is a cross-section. If it's not given, find the limits of integration, and then finally integrate. We're going to look at this first example. It says the base of a solid is bounded by the curve y equal to the square root of x plus 1 and the x-axis on the interval from 0 to 3. The cross sections are half circles with diameters perpendicular to the base. Find the volume of the solid. So again, this is just a bunch of words. So what I'm going to do is I'm going to graph this. We're going to graph y equal to the square root of x plus 1. And then our x-axis, but we're only concerned with x values from 0 to 3. So let's see what that would look like. We have this y function. And we're only going to be looking at 0 to 3. So this is our region that we're concerned with. This region is what they're referring to as the base. This is our base of our volume, and we're going to create the volume by creating these half circles whose diameter is perpendicular to our base. So I'm going to go ahead and just draw a representative half circle. It would look like this. A diameter, and then the half circle is going to come up. That would be our A of x. So imagine that we have all these half circles that we're creating. And what we'll end up with is this volume. So we're going to create a volume. What our integral is going to do is it's going to add up all these half circles from x is equal to 0 to x is equal to 3. So the first thing I want to do is I want to look at a representative cross-section, and I want to figure out the area of that cross-section. So this is a half circle. Its area is going to be 1/2 pi r squared. Now I have to figure out what r is. So r, our radius, is the halfway distance. When you think about this, the whole distance, this diameter, is just our y function, which is the square root of x plus 1. So if I was going to find a formula for my radius r, it would be half of the square root of x plus 1. So each of my cross sections will be the area of a half circle, which is 1/2, pi. My r is the square root of x plus 1 squared. So if we clean this up, over 2. So if we clean this up, and this whole thing is squared, ooh, terrible notation, then I have 1/2 times pi times 1/4 x plus 1. Or in other words, pi over 8 times x plus 1. So that's the area of my cross section here. I'm going to add up all these cross sections to create a volume. And then my volume becomes the integral from 0 to 3 pi over 8 times x plus 1 dx. Now the pi over 8 is a constant, so I can go ahead and pull that out and integrate x plus 1. This will be pi over 8 x squared over 2 plus x, and I'm evaluating this from 0 to 3. Which would be pi over 8, 9 over 2 plus 3. And then minus a 0, but that's just going to be 0. So I believe this is going to be 15 pi over 8. Double check me on that computation. So the general slicing method, you're going to be given a function that will give you your base area. And then from that, you're going to look at a cross section. So the cross section has to be described to you. In our case, we're looking at cross sections of half circles. So I had to figure out the area of half circles and add them up over my base. What's really helpful in these sections is to look at the textbook, the animated textbook on MyLab. They have very, very nice images that are animated where you can actually change the cross sections and create your volumes. That was a general slicing method. There is a particular slicing method that we call the disk method. So what we're going to do now is we're going to create a volume by taking a function and rotating it about either the x-axis or the y-axis to create our volume. When we rotate about the x or the y-axis to create our volume, our cross sections will always be circles, which is why the a of x is the area of a circle, which is also called a disk. So each cross section will be a circle, and then we'll go ahead and add up all those circles by integrating. Example 2 says we have a region. It's bounded by this curve, x squared plus 1. The x-axis, lines x is equal to 1 and x is equal to 2. So we're going to find the volume of the solid obtained by rotating our region about the x-axis. So again, what I'm going to do is I'm going to sketch this. Our function is x squared plus 1. But remember, we're going to bound ourselves by the x-axis, the lines x is equal to 1 and x is equal to 2. So really I'm looking at this parabola opening up, it's shifted upward. But I'm only concerning myself with the values from x is equal to 1, that line, and x is equal to 2. This is my region. So I'm going to take this region and I'm going to rotate it about the x-axis. And when I do that, I'm going to be creating this volume. So this curve is going to come down, and this is supposed to be a mirror image. Forgive my drawing. So what I've done was I've created this volume. By rotating my curve about the x-axis. Where each of these cross sections in my volume is a disk, right? So it'd be here. So I'm going to add up the area of these disks, or these circles. I'm going to add them up from x is equal to 1 to x is equal to 2. So think about what this radius would be. Our radius is going to be equal to the distance from the x-axis to the function, which is just x squared plus 1. Our volume is the integral from 1 to 2 of the area of each disk or circle, which is pi r squared. Pi, r is the function, x squared plus 1. We square that. Pi is a constant, so I'm just going to bring it out, and I'll deal with that later. When I multiply out, the x squared plus 1 squared, I get x to the 4th plus 2x squared plus 1. Integrating, this becomes pi times x to the 5th over 5 plus 2x to the 3rd over 3 plus x. And I'm evaluating this from 1 to 2. So it's always upper minus lower. If I put in 2 for x, it looks like 32 over 5 plus 16 over 3 plus 2 minus 1/5 plus 2/3 plus 1. After we do the math, I believe it's going to be 178 pi over 15. Again, you can double check me on those computations. I'm just more concerned with how you set this up. So don't forget, your animated textbook on My Lab has some really great figures that you can create volumes with. So they're very interactive. So you should try that if you're not understanding what your volume is supposed to look like. The last method in this section is called the washer method. And we use the washer method to find volumes when we have two functions. And one function is greater than or equal to another function on some interval. The cross sections are still going to be circles or discs, but they might have a hole in them, which is why we call them a washer. It may look like a washer. So to figure out the radius, what you do is upper minus lower, but you have to square it because this whole thing is r squared. Example 3, we have a region. It's in the first quadrant. So first quadrant means I only have to graph the first quadrant. So the region is in the first quadrant. It's going to be bounded by the curve f of x equal to x plus 2 and g of x equal to x squared. and the y-axis. Now we don't actually have to have that word y-axis in there because we already know it's in the first quadrant. So the f of x plus 2 is going to be a line. I don't really care about what the line is in the second quadrant. I'm only concerned with the first quadrant. G of x is just a parabola opening upward with the vertex at the origin. So it's going to look like this. And in between those two, that would be the region that we're referring to in the first quadrant. So what we're going to do with this region is we're going to rotate this region about the x-axis. And this may be difficult to visualize, but what's going to happen when we rotate this around is we're going to be creating this volume where there's actual hole in the middle, which is why we use washer. Now I'm just sketching this so it looks kind of sad, but this would be the volume that we're creating, where cross sections are still discs. But notice that they have holes in them, right? It's just these pieces because there's this hole in them. So we have to figure out the radius for each piece. And the radius for each piece is going to be the upper function minus the lower function. It's exactly what we did in 6.2 when we were finding areas. I'm not given limits of integration. I know it's in the first quadrant, so I know I'm going to be starting at x is equal to 0. To figure out where my limit of integration ends, I have to figure out the intersection between these two functions. So if I set them equal to each other, x plus 2 equal to x squared, this becomes a quadratic equation set equal to 0. Which factors as a minus 2 and a plus 1. So I have x is equal to 2 and x is equal to negative 1. Well, we're only concerned with the first quadrant. So we're going to integrate from 0 to 2. And our volume will be the integral from 0 to 2 of pi. We're going to take upper function. The upper function is the line x plus 2. Square it and subtract the lower function, which is x squared. Square that. And then integrate with respect to x. Again, I'm going to go ahead and pull the pi out and integrate from 0 to 2. Once I multiply all this out, it'll be x squared plus 4x plus 4 minus x to the 4th dx. Antiderivative would be x to the 3rd over 3 plus 4x squared over 2 becomes 2x squared plus 4x minus x to the 5th over 5. And here we're integrating from 0 to 2. Putting in 2 for x, I have 8/3 plus 8 plus 8 minus 32 over 5. And then we're subtracting 0. So again, I don't even have to write that. After computing, I have 184 pi over 15. Okay, again, double check me on those computations. That's actually not the main focus here. The main focus is setting these up. In section 6.2, we looked at areas where we integrated with respect to x, and we also integrated with respect to y. We're going to do this with volumes as well. So this upper formula, that would be integrating using the washer method with respect to y, and the lower formula is integrating using the washer, or the disk method, sorry, with respect to y. So here we have a washer and disk. So we'll look at one example where we are using the disk method but integrating with respect to y. Our region is going to be the curve x squared minus 1. It's going to be bounded by the y-axis. The line y is equal to 0, and the line y is equal to 1. So first off, I want to sketch that. X squared minus 1 is a parabola that opens up. Vertex is actually below the x-axis. Okay? And we're looking at a graph that's bounded by y is equal to 0 and y is equal to 1. So I'm only concerned with not the bottom part, this part here of my graph. So this is my f of x. So we have y-axis, y is equal to 0, y is equal to 1. Sorry, y is equal to 1, and our function. This would be our region that we're going to rotate about the y-axis. Okay. Sorry. So if we rotate this about the y-axis, we're going to create this volume where we have our disk. Each disk has a radius, except for this value r is actually an x value. So if f of x, or y, is equal to x squared minus 1, since we're integrating with respect to y, we have to solve this for x, which gives us x squared equal to y plus 1. X is equal to plus or minus the square root of y plus 1. And now, since I'm only concerned with positive x values, I'm choosing x to be equal to the square root of y plus 1. That is going to be my radius r. Putting this together, our volume, with respect to y, is going to go from 0 to 1, which are our given y values. Pi, r is the square root of y plus 1 squared dy. I'm going to pull out the pi and integrate y plus 1. Oops, sorry. Pull out the pi, integrate from 0 to 1 of y plus 1 dy, which would give me y squared over 2 plus y from 0 to 1. And I have pi times 1/2 plus 1 minus 0, so I'm not going to bother writing that. I end up with 3 pi over 2. The last example we're going to look at is what happens if we have compound regions. So now this is not necessarily going to be with respect to x or y. I'm going to look at it first and then decide. Okay, so I have a region R. It's going to be bounded by this f of x, 2 minus x, and g of x. So I have two functions. I'm going to be looking at x values from 0 to 2. If Find the volume of the solid formed by rotating about the x-axis. So since I'm rotating about the x-axis, this tells me that my integral will probably be with respect to x. So let's look at what this region looks like. 2 minus x, that's going to be a line. Let's see when x is, or we're at 2, so it's going to be a line that does this. And then g of x is the square root of x. Okay. So the region is bounded by these two curves from x is equal to 0 to x is equal to 2. So at 2, we're at this point here. And since it's between the curves, it would be this first region and then this second region. But notice that the upper and the lower functions have switched. So I have to figure out where they intersect. And then I'm going to set up two integrals. Again, we're going to be rotating about the x-axis, which tells me I'm going to integrate with respect to x. 2 minus x equal to the square root of x. I'm going to go ahead and square both sides. And then multiplying out, I get 4 minus 4x plus x squared equal to x. It's quadratic. If I set it equal to 0 and factor, at least I hope it factors, it looks like it should be a minus 4 minus 1. So x is equal to 4, x is equal to 1 is where these are going to intersect. So this must be 1 because it has to be between the 0 and the 2. So I'm going to set up two integrals. I'm going to find the volume of this first region by integrating with respect to x from 0 to 1. And then I'm going to find the volume of the second region by integrating from 1 to 2. Again, the only reason why I have to set this up with two integrals is because the upper and the lower functions have changed. So my volume is going to be equal to the first part, integral from 0 to 1 of pi. My r squared is going to be the 2 minus x squared minus the square root of x squared dx. Then I'm going to add this to the second volume from 1 to 2 pi, and now my square root of x is the upper function, so that would be the square root of x squared minus 2 minus x squared dx. So it's just a matter of doing the computation. Again, I'm going to pull out the pi and integrate. After I multiply everything out and clean this up, I get x squared minus 5x plus 4 dx. And I'm going to add it to, pull out the pi, integral from 1 to 2. After multiplying everything out here, I get a negative x squared, so it should be opposite of what the first one was. Negative x squared minus 5x, plus 5x. Messed up my sign. Minus 4. First integral will be x to the third over 3 minus 5x squared over 2 plus 4x, evaluated from 0 to 1, and then I'm going to add it to pi times negative x to the third over 3 plus 5x squared over 2 minus 4x from 1 to 2. So our computations will give us 1/3 minus 5/2 plus 4 in this first integral, and then minus the 0, so I'm not going to bother to write that. But the second integral, I don't have 0 as one of my limits of integration, so it'll be a little bit longer. Be negative 8 over 3 plus 5 times 4 is 20 over 2, 10, minus 8, minus negative 1/3 plus 5/2 minus 4. All right, so after I do all of those computations, what I got was 3 pi. Seems like a lot of work for 3 pi. That's it for this section, and I really recommend that you look at the animated figures in your e-text on MyLab. They're really great.